So let's say a few words about this figure. So yesterday we talked about when we have the particle oscillate like this particle, okay, particle oscillation this way, see air motion like this. And funny thing is, people say they cannot see clearly of the pointer, so want me to use mouse. I wanted to do we have something so I don't have to do this because they say they cannot see clearly. They want to do this. Okay, so no wonder I cannot become Kyaku. Okay, we got to do this. Yeah. I wonder if we have something like this so I can do it higher up. Maybe that. Yeah, okay. Okay, so then we have particle motion like this, and then you see the wave propagating to the right and lower corner, and in the meantime, the wave velocity is propagating in this direction. Okay, and this Cp, the phase speed, and wave velocity can be calculated based on the equations. Okay, remember we have based on those equations, based on the dispersion relation. Remember we derived that dispersion relation like this. Right, we have dispersion. Can you see clearly? Sorry, my writing become terrible because of these markers. Okay, so dispersion relation. Okay, so dispersion relation is omega, assuming U is equal to 0. Okay, so then capital omega, that's the, by the way, what's capital omega? What's that? What's omega? Capital omega. Capital omega. What's that? This capital means 大写. Okay, omega. What's capital omega? What's the meaning of capital omega? Anybody knows? It's Doppler frequency, intrinsic frequency. This is frequency, right? This is frequency, right? And this one, you subtract the U, okay? So we should call the Doppler or intrinsic frequency. Okay, so now if U is equal to 0, then omega equals to omega. Okay, the capital omega equals to small omega. Okay, what means capital omega? Okay, capital omega, that's equals to, that is omega. That's English. Okay, that's English. Okay, 大写. Okay, yeah. Small letter is 小写. Okay, or sometimes we call uppercase, that's 大写, or lowercase, that's 小写. Okay, now, so we have this equal to this, then omega is equal to k times n. Okay, and then square root k squared plus m squared. Okay, so now we can calculate based on this dispersion relation. We can calculate Cpx. That means the phase speed in x direction. Okay, So that equals to omega divided by k. Okay, and we have positive, negative. Okay, we have two waves. And that gives us positive, negative n divided by square root k squared plus m squared. Okay, and then C sub pg is equals to omega divided by m. Okay, this is horizontal wave number. This is vertical wave number. And that gives us the following. Okay, divided by m, right? So we have positive, negative k times n divided by m times k squared plus m squared. Okay, and also we can calculate group velocity. Okay, this is phase speed, or you can say phase velocity. Okay, and also group velocity. So we have cgx and cgz. Okay, and that we calculate down below here. Okay, so we have this equals to partial omega partial k. This is equals to partial omega partial m. Okay, and that will be equals to, okay, plus minus m squared times n divided by, okay, k squared plus m squared, and then 3/2. Okay, you don't see clearly here, you probably can just see from there. Okay, that's very clear. And this equals to negative k m times n divided by k squared plus m squared to the 3/2. Okay, to the 3/2. Okay, so based on this, then if we decide, okay, just choose one example. If say, for example, if assuming k is greater than 0 and m less than 0 and omega greater than 0, okay, just one example. You can choose different signs you want, just for example. Then, okay, then based on this, Cp, x and Cpg, okay, then we can find the Cp like this, okay, that has two components, and this vertical component will be Cpg and Cpx, okay, so two components that give us Cp. So that's the direction we have. Cp, phase speed, is based on our calculation of omega divided by k and omega divided by m. Okay, so then we can determine the direction. And then you also can do that for the group velocity. Okay, you do this, and then that gives us that direction perpendicular to it. Okay, and that that has a special characteristic we call, in this case, k dot v prime, k dot v, okay, v prime, like this. Okay, it's equals to 0. Okay, what does this mean? Okay, because k has two components. No, k is the vector, so that gives us small k times m in x direction, in z direction. Okay, this is horizontal wave number. This is vertical wave number. Okay, and then dot product of this one, v prime, we have u prime, right? And then w prime, okay, equals to 0. And what's this? The dot product. How do you say dot product? Net g. Okay, I can still remember. Amazing, yeah. Okay, I majored in math when I was in college in Taiwan. Okay, so you do 内积 inner product of these two. What do you have? Yeah, K times U prime. Right. But in other words, they are perpendicular. Okay. You don't need to do it. Okay. Okay. It's pretty simple. Okay, right? Okay. It's K times U prime plus M times W prime. Okay. So, okay. I'm kind of, okay. I think I need something here, so I become calcu. Okay. Yeah. Okay. Oh yeah. Okay. Good. It's good. Thanks. Okay. So when you have this, simple way to say is the K that's a vector. This K is a vector. It's equals to Km. Oh, thank you very much. Okay, that's good. Okay. Okay, that's smart. Yeah. Okay, thank you very much. Okay. Yeah. Thank you. Can you see it? Oh, here, come. I cannot see it. Oh, here, okay. So when K dot product of V prime equals 0, that means that's called a kind of transverse wave. Okay, so let's see what is K. Okay, V prime is equals to U prime and W prime, right? That's a vector. Okay, and U is horizontal motion, but okay, W is vertical motion. Together will be the actual motion. So that will be equals to this. Okay, equals to this air motion here. Not stable. Okay, like this. In motion. Okay, so you have horizontal motion, air vertical motion together give us this centerwise tilted motion. Okay, and that is K, right? That is V. That's V. Okay, that's V. Okay, U and W. That's V. And V dot product of K. What's K? K is this. This is K. See here? This is K. This is K. Okay. Maybe I just go there and point it. Okay. Here's. I think people probably can see it. My finger. Okay. So K here. So K here, and then air motion this way, and air motion this way. This is V prime. This is V prime. Okay. And K is. This is vector. This is vector. Okay. And this is composed by small k and m. Okay, so this is go this way. So it's perpendicular. So your air motion like this, it move like this way, but wave go this way. Okay, it's unlike the other type of wave you are very familiar with, like our sound wave. Sound wave, we compress it. Okay, we compress it and expand it. And then with oscillation like this, and then wave will go, okay, in the same direction as motion. Okay, right. But here you got the air motion like this. Okay, V, and then the K product of V will be 0. That means perpendicular. So the wave go this way. So kind of strange, right? Okay. So it go vibrate this way, and then wave go this way. Okay, that's called transverse wave. I think I learned that probably from some basic wave dynamics. Okay, so let's try to explain this transverse wave. And then last time, yesterday we mentioned these properties has very important application to the numerical weather prediction. Okay, because when we have a numerical weather, numerical prediction, we have a kind of vertical domain and then at top, the lateral boundaries, we need boundary conditions. Okay, and then in the horizontal, okay, since our CPX look at and CGX, the X component of CP and CG are same direction. They are not equal, but they are same direction. You're positive there, you're positive there. Okay. See here, you will have positive here, you have positive here. You will choose the negative. Here there are two solutions. You choose this negative solution, and here you choose the negative solution. Then they are same direction. So no matter it is to the right or to the left, they are same direction. Okay. So then you can apply the advection equation to advect the wave energy out, because wave energy goes with the groove velocity. Okay. You can have the wave propagate this way, but energy propagate different way. Okay, like we see in that figure. Okay, so then in horizontal they are same direction. So then the domain boundaries, you can apply the advection equation. Okay, to advect the wave energy out. So make it simpler. Okay, so how many of you are aware of, maybe some of you haven't taken the NWP course yet. Okay, for some people, how many of you have taken NWP courses, modeling courses? You, okay. You, okay. So what kind of lateral boundary conditions do you use in OFF model? Yeah. In the regional model, what the lateral boundary condition? We call open boundary condition. Right. That's you using advection equation to advect. Okay. Variable out. Yeah. The energy out. Okay. But in vertical, my point here is this: you look at in vertical direction, you have positive, negative. So you choose positive, the upper one. Here you have to choose the top one, that's negative. So in vertical direction, they are just opposite. Okay, so you see wave looks like going up, but the wave energy could go down. They are opposite. Okay, because wave energy goes with the groove velocity. Okay, and phase velocity is the wave, what you see. Okay, you can see wave propagating, that is phase velocity. The groove velocity is not necessary to be in the same direction. Okay, so that's funny thing about the gravity waves. Okay, make it very difficult to understand.
How do we know the energy propagation is related to the velocity?
Yeah, you can prove it. You can prove that that based on the Pohm, Elias and Pohm theory. Okay, that we probably will touch upon that briefly. Okay, so briefly speaking, we can apply this equation. This phi can represent any variables in your model. Okay, like U, like V, like W, like P, like theta. Okay. So when you apply this CPX, okay, yeah, you basically apply this advection equation that you can advect the energy out of your domain. Okay. And in vertical advection equation, if we apply a vertical advection equation, we cannot advect the wave energy out of the upper boundary. Okay, because these two are in kind of opposite direction. Okay. Okay. Any question? That's wave property. Yeah. Because we derive this, okay, from the governing equations. Okay. And then we apply normal mode approach. Okay. Remember we apply that. Okay. Because every system, like shallow water system, like the surface fluid system, they have different governing equations. The governing equations are controlling the wave motions. Okay, so based on that, we derive the dispersion direction. And based on this, we calculate this, and we found they are just in. Okay, these two, okay, are in the same direction, but CPG and CGG in vertical, they are in opposite direction because of wave property, because of the system are different. Okay. Yeah. Like maybe one simple way is like this. Okay, one more time, like the sound wave. Okay, you squeeze, you release, you squeeze, you release, oscillate like this, and the wave propagate in same direction. But if you go to a lake, or ocean, okay, you jump, okay, the wave is not going up and down. Okay, right. You just kind of oscillate in the ocean or in the lake. Where does the wave go? Goes out. Yeah. So this is wave motion. No, this is your wave motion, but this is your vertical motion, your particle motion. Okay, like your particle motion. So you just jumping down and up and down in the lake. Okay, the wave is not going up, going down. Okay, that's your particle. Okay, your air motion, fluid motion, and then okay, the wave goes horizontally. Okay, that's perpendicular, like we said. Okay. Okay, so if we apply this vertical elevation equation, we cannot elevate the wave energy out because they are just in opposite direction. Okay, group velocity. Okay, wave energy propagation is associated with group velocity. Okay, and phase velocity is what you see. Okay. Okay, so that so then we normally, okay, I'm not going to go to detail in that, but just briefly speaking, in the numerical weather prediction model, NW model, the arithmetic vertical, normally most popular boundary conditions at top. Okay, at top, okay, the sponge layer, okay, which increase the viscosity to absorb energy out. Okay, because you don't want energy produced, okay, in the domain. Okay, so as I mentioned briefly yesterday, if in the beginning we assume W prime equals to W hat, that's a function of G. So here is only a function of X and T. Okay, and if we assume W hat is also kind of wave-like disturbance, then we can assume we have this W naught. This will be constant, not a function of anything, not a function of T, X, and G. Okay, so it's a constant, and times, okay, because it's only function of G, right? So we have this, assuming in G direction, we have the oscillation, so e to the I m G. Okay, M is called the, what's M, by the way, what's M? Vertical wave number, very good. Okay, wave number. So then you put this, substitute this into there, then you get, you substitute that into there, then you get this W prime, okay, equals to W naught e to the I mg, okay, this is W hat of G, okay, times e to the I kx minus omega t. Right. So together will be w naught e to the I. We combine these two together, become I kx plus mg minus omega t. Okay. And since here we do this first, and then we do this, but actually you can do it as I mentioned yesterday. You can do it one time. Okay, just substitute that expression into it. That's called normal mode approach. Okay, then we get the same result. And then if you do that and then take the real part, no matter what you do with a normal mode approach, normally you probably will get the result with real and imaginary, okay, complex number. But for the real atmosphere, real physical phenomena, okay, we have to get rid of the imaginary part. So that's why we take real part here, okay. And then you do that, you get this, okay. You get the W in terms of this cosine, sine of kx mg omega t, like this. And then you can derive this theta prime. Okay. You can derive theta prime. I'll give you a quiz. Okay. How do you get theta prime? Okay. Theta prime we can do it, right? Because that's what we do. Okay, here. Okay. How do you get theta prime? Okay. Right. This one we know how to do it because okay, we just take real part of this and then we get these two, and W okay, WR and WI are real and the imaginary parts of W naught. Okay, so there we assume so W naught is equals to WR plus I, WI. Okay. So this is complex number. This is the real part of W naught. And this is the imaginary part of W naught. Okay, and times I. Oh, I think that's why I asked for the book, because this takes too much time to search for it. And here I cannot do search. Okay. Can I do search here? Yeah. Too much work. I probably just go to the book, okay? Too much work. That's probably why I asked for the book. Oh, I forgot to get it. Yeah. Okay, could you? Yeah. 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 Yeah, on the table. Okay, so I show you how to do it. Okay, I got it here. Okay. So say if we have W prime, okay, real part of W naught e to the I kx, okay, and then plus mg minus omega t, and then we get something, right? Okay, so now if somebody asks you, okay, once you get this, can you get theta prime? Okay, so in order to get theta prime, you go to the original equation here. Okay, and where is theta prime? Where is theta prime? Which one? Which one? 3.5.4. His W prime, theta prime. Okay, so in order to find theta prime, okay, but this is wrong. Okay, we have to find the relationship between W prime and theta prime, the equation. And the equation is partial theta prime, partial t, plus u, partial theta prime, partial x. Okay, and then plus n squared, and then theta naught divided by g, and then W prime equals to 0. Okay, and remember when we are discussing, when we discuss this, we did, okay, a special case, we did it's omega equals to small omega minus ku. Okay, we assume u equals to 0. Remember that? So here it's gone. So we only very simple equation. Okay, so then first thing is you apply normal mode. Okay. Can you guys work out for me? Okay, normal mode. You apply this normal mode. Okay, what's the equation? What's the equation in the wave number space? Can you find that equation, transfer that equation into the wave number space? Similar to what you did for more complicated cases like in Fourier space. Okay, okay. So this equation is in that physical space. You try to convert into the wave number space. Okay. Remember I said that the ddt is corresponding to what? Minus I omega. Okay, and this is okay, right? So this become negative I omega theta. Okay, negative I omega n square theta naught divided by omega g. So we have this, and then W prime. Okay. So now we know W prime, taking the real part like this, we just substitute in. And then we get the theta prime in the wave number space. Okay. So that's what see here, if we did W prime equals to W hat e to the ikx, and then substitute this into there, we get that W prime equals to W naught e to the I times kx plus omega, plus mg minus omega t. Okay, we substitute in there and then take the real part, we got W, okay? And then we have W naught equals to W sub R plus I, W sub I. And that gives us this. And then here, we just substitute into it, okay? Yeah, okay, we just substitute into it, okay? See that A square, theta naught, okay, right? And that omega G, see there? We have theta naught n square g omega. Okay, and of course you have to take real part. Okay, yeah. Okay. Anyway, so then you can substitute W prime into 3.5.1 to equation 3.5.4. Okay, assuming u equals to 0. Okay, this is what I did. Okay, in 3.5.4. Okay, and you can do it for p prime equation and other equations, so you get this. And this is called polarization relations. Okay, and then they relate. So once you get solution in W prime, you get solution in U prime, P prime, and theta prime. Okay, so That means if you like, you can combine equations into one of p prime or u prime or theta prime you like, and then you based on this polarization, okay, relation, then you can get other variables, okay. Okay, so, okay, probably let's go back to here. Let's go back here. I think we stop here, okay, yesterday. So then let's take 10-minute break and then come back and we start from here, okay. Okay, so let's go back to the solution 3.5.8 and 3.5.9, okay. And as we discussed yesterday, it depends on your n square over omega square greater than 1 or less than 1. You have two different solutions and you have two different behavior. Okay, upper one and lower one, they represent different wave regimes. Okay, so what is the upper one represent which kind of wave? Which kind of wave regime? Vertically propagating wave. Wave can propagate vertically. This one is evanescent wave. That means it cannot propagate vertically. So wave energy is affected by the flow, via flow stronger. Okay. And so now, okay, so for n square over omega square greater than 1, then the wave can propagate vertically. That's called the vertically propagating. Okay, waves. And for the second one, okay, second case, n square over omega square less than 1. Okay, and you cannot see wave. So say for example mountain, you cannot see wave. You become kind of flattened up. It's weakened with height. So here we have evanescent. Okay, flow. Normally we say flow. Okay, yeah. Because you don't have oscillation, we just say flow. Okay. Some people say waves. That's okay. Okay, now we want to look at extreme case. Extreme case. So n square is greater than omega square. Okay, we go to extreme. Okay, not equal. Okay, not implies. So for extreme case, okay, then n square is much greater than omega square. Okay. Then in this case, okay, this is okay, kind of buoyancy oscillation. Okay, is buoyancy oscillation is much greater than the frequency, the intrinsic frequency. Okay, so that's so this imply n much greater than omega. Okay, it's implied like this. Okay, we just, for example, just look at the positive one because this is supposed to be positive negative. Okay, and then we just look at positive one. We got this. And this gives us 2 pi over omega, not omega, 2 pi over, okay, 2 pi over, yeah, omega, and much greater than 2 pi, okay, over the, let me see, 2 pi, no? 2 pi over T of the buoyancy oscillation, okay, and 2 pi over T of advection, okay, like that. So this means T advection is much greater than T buoyancy. This means, for example, if say we have a mountain like this, and if this flow speed is very small, then this will take a long time to passing over. Passing over. So then it allows the air parcel to be influenced by the mountain to do vertical oscillation, forced up oscillation, and then oil can propagate upward. Okay, in this case, okay, in general case can be vertically, can be upward or downward. In general case, it can be vertically propagated, not only upward. Okay, sometimes you have like a bump there. Okay, you can have oil propagate upward and downward. In other words, it's vertically propagating oil. Okay, it's much greater, so you don't have that. Okay, so in this case, constant phase lines and the groove velocities are oriented vertically. Okay, so in this case, okay, the constant phase lines and the groove velocity is n squared much, okay, oriented. Okay, total oil number vector is oriented horizontally. So you have groove velocity, okay, CG, go like this, and CP, go like this, perpendicular, but this is go vertically, okay. And so oil energy purely go upward, not this way, not this way, okay, purely go upward. And in this special regime, we call it the hydrostatic gravity wave regime. Okay, and so here the vertical momentum equation is 3.5.2. Okay, we're reduced to this not important. These two are in balance. Okay, this not important. The vertical acceleration is very small. Okay. Okay, so it becomes this. Okay, like this, and you can. Let me see how do you see this? How do you see this? Let me give one. Okay, let's look at the governing equation. Remember we have 3.5. I can derive it. Okay, I can derive it. Okay, so remember we have this the Taylor-Goldstein equation. Remember that? Okay, you got your note. It's 3.5.5. 3.5.5. Okay. So you look at that, 3.5.5. Okay. And that is partial t plus u partial x square. And then we have d square w prime dx square plus d w prime dg square. Okay. And then plus n square. And then d square w prime dx square equals to 0. Remember that? The governing equation. Okay, and then I'm not going to repeat it. Okay, then we derive this. We assume W prime equals to W hat of G e to the I of kx minus omega t. Okay, then we derive this equation, d square W hat dg square. Okay, and then plus n square over omega square minus 1, and then W hat equals 0. Remember that? That is which equation? Which equation is this one? Look at it or not. Which equation is this? 3.5.7, right? I think I will discuss this, right? Because those are based on the solution of this one. Okay. Okay, now, so if a square greater than omega square, okay, a square is much greater than omega square. What does that mean for n square divided by omega square? Greater than 1, much greater than 1. So this term is much greater than 1. So what happened to this one? Doesn't matter. We can ignore it, right? So that's good. Okay. So now this implies if n square and omega square much greater than 1, then this equation will become d square W prime dg square plus n square over omega square W hat equals 0. Approximately, we get this. Okay, we get this. Yeah, right. That's good. Okay, and so in other words, this equation can also be written as W hat of G square, and then plus n square minus omega square. Okay, and then you divide by omega square times W hat equals 0. Okay. Yeah. Agree? Okay. So where does n coming from? Where does n come from? N is buoyancy, the buoyancy frequency or Planck vessel frequency. Where does it come from? It comes from the buoyancy force, right? Okay. Yeah. Which term is buoyancy force? Huh? Theta prime. Theta prime. This buoyancy force. This gives n. Okay. And omega. Okay. Omega is equals to small omega minus k u. Okay. Where does this coming from? Where does this come from? From that equation. Very good. Partial W prime, partial T, right? This gives you omega, right? Remember, in the physical space, the T, in the wave number space, this partial T become negative I omega. Okay, negative I omega W prime. Okay. Okay, this become negative omega. So that one gives us negative I omega. Okay, and how about this one? U partial W prime partial X gives us I K U W prime. These two together gives us what? I, okay, give us negative I omega, okay, and then plus I K U, 30 prime. If we pour negative I out, will be omega minus what? Ku. Right. So this term, okay, what's this term? What's this? Capital omega, okay, uppercase, okay, omega, okay, and so this term is coming from, this one coming from the buoyancy force. This coming from what? The first two terms. Okay. Yeah. So now, if n square is much greater than omega square, that means these two terms is much smaller compared to this term, the effects. Okay. And then if we don't have this, then what's that equation called? Hydrostatic. Hydrostatic. Okay. That's why, okay, that's more or less improved what I said earlier. Okay. So it's reduced. So this will reduce, okay, this vertical momentum equation will reduce to this. Okay. So what's the physical meaning of this term? Left hand side. Pressure gradient force in vertical direction, or vertical pressure gradient force. Okay. And that is balanced by buoyancy force. Buoyancy force is related to gravitational force. Okay, balance. Okay, yeah, that's hydrostatic. Okay, so this is extreme case for n square much greater than omega square. Okay, so your vertical, okay, oscillation, vertical buoyancy force is much stronger than advection. Okay, yeah, because it's advection so slowly. So advection force is much smaller than this vertical oscillation, okay, the buoyancy force. Okay, so then your oscillation, you got chance to oscillate, okay, because mountain is so wide, okay, or wind is so slow, then you got chance for particle to get vertical oscillation, and then you get wave energy, get up or down, okay. In this case, your mountain will go up. Okay, so this implies that, okay, the probably pay attention to here. This implies the vertical acceleration, the W prime, the T term, okay, the W T term, okay, plays an insignificant role in wave propagation, okay. So that means the, okay, elevation terms playing kind of insignificant role compared to this vertical oscillation. This vertical oscillation. And this one is trying to balance this one. Okay. Okay. Okay, very good. So now, and actually you can trace back to the equation. Okay, these two terms. Okay, if you don't trust me, okay, you go home. Okay, you go home, and when you derive equation, and then you try to pinpoint this omega, and eventually you can trace back that omega is related to that, okay, partial t plus u partial x terms, okay, and that can be ignored if buoyancy force is playing dominant role, okay. Okay, so that extreme case will reduce to, let me see, reduce to, okay, so this will reduce to, the extreme case will reduce to, let me use a different color. So this will reduce to the, okay, hydrostatic. Okay, wave. Okay, So extreme case. This. Okay. So that that partial t, okay, term plus u or partial x term is very small. Okay. Effects compared to buoyancy force. Okay, now another extreme case. Another extreme case is just object n square much less than omega square. And this one is hydrostatic gravitational wave is vertically propagating wave. Okay, so hydrostatic wave is always vertically propagating wave. Okay, the growth velocity is always vertical. Okay, pointing vertically. Okay, so like for example here, in a general case, you look at here. In this general case, the growth velocity is not necessary to be purely vertical. But if the gravity wave, if the buoyancy force become more and more dominant, this theory will become more and more vertical, eventually become vertical. Then that's extreme case. Okay, yeah. That's the hydrostatic gravitational waves. Okay, now you look at the other extreme case here. Then what happened? Then here is the W head dg square will become negative 1 minus n square divided by omega square divided by W head equals to 0. Right? It's the same equation, but we just flip-flop because in this case we have n square over omega square is much greater or much less than 1. Much less than 1. Okay, so this is much less than 1. That means this one is almost 0 compared to 1. Right? Then this equation can be reduced approximately. Okay, equals to what? Minus W head equals 0. It's interesting. And disappear. Okay? Right? And disappear. Okay. And in this case, the solution also very simple too. Yes. Which one? I think we have K here, right? Yeah, right, that's good. Yeah, very good. Okay. So K square here, and then K square here. K square here. Okay. Okay, remember here. Remember here, the dt is corresponding to what? Negative I omega, right? Negative I omega. And ddx is corresponding to what? In Fourier space? Okay. So now, if somebody asks you, if we have an equation like this, in the Fourier space or wave number space, equals 0. If somebody asks you to recover this equation from the physical space, how do you write it? Okay, try it. Okay, try it. Okay. If somebody gives you an equation in Fourier space or Fourier number space and ask you what's the equation look like in the physical space, try it. Okay, I'll see if anybody can figure it out. Don't look at the note though. Okay. So if you see something, like I omega, okay, then you know it is related to partial t. If you see something of past ik, that will be related to what? TTS. Right. Okay. So do we see IK there? That equation I asked. We don't. Too bad. Okay. That's right. Okay. You cannot get something so simple. Okay. But we do have what? We do have a k square. Right? We do have k square. Right? We do have k square. So we don't have ik, but we have k square. Okay. So is this related to okay, ik? Square. Okay, square. So this is related to ik square. Ik square related to what? Twice. Okay, twice. Okay. So then this equation, can be converted into physical space as the square w hat the x square, and then because we convert, so we no longer have hat, and then plus the square w dg square equals to 0. Equals 0. So look at this equation. This is the original equation, and this is what we recovered. Are they related? Yeah, they are, right. Because if n is small, very, very small, this is buoyancy force. It's very small. This is gone. And then this, you integrate it, you get this equal 0. That's this one. So we have two extreme cases. One extreme case is when this term is very small, because this term times this one is advection, and this is vertical motion, oscillation, this is vertical oscillation. So then we got, extreme case like this. That is hydrostatic gravity wave. That exertion, the advection term is related to partial t plus u partial x and this term. like this. Okay, now that so right now if n square buoyancy force is small, then this will be almost zero compared to this one. And then this one will reduce to this equation. Okay, and this is a Poisson equation, right? Okay, and what kind of flow is that? That is our friends. That's our friends in engineering. Okay, okay, like the most. Okay, because in their case they don't have much certification, because like they study like probably river flow. They study like a kind of fluid in an engineer, okay, like a pump, okay. They don't care about certification. If you don't have certification, you don't have n square, right? You don't have buoyancy force, okay. And so then they reduce that. That's called potential flow. Potential flow. That's the extreme case, okay. So then we have kind of two extreme cases, okay. The vertical oscillation wave regime will reduce to hydrostatic gravity wave, okay. And the equation here will become, the equation here will become d dt plus u ddx square, and then partial square w prime partial z square plus n square partial w prime partial x square equals 0. That's the extreme case. Okay, so this ddx is not important because this term is related to that, okay, advection term. Okay, that give us the vertical acceleration. That term is ignored. And other extreme case is like this one, give us potential flow. Okay, and so that's what our engineer friends are studying most. Okay, of course, there are some engineers like fluid dynamics. They also study very interested in our case, like the buoyancy force. Okay, like the certification case. Okay, and the biggest differences of what we are doing, the atmosphere physics, dynamics, ocean dynamics, or GFD, geophysical fluid dynamics. The major difference of geophysical fluid dynamics from the general fluid dynamics like engineering people are doing, the big difference are two. One is certification. We have certification because we have huge, space, scale of the motion. Okay, so then gravity wave come to play, and then the denser fluid start to accumulate at door, there, and then become lighter. And in engineering, they don't care much about that. Okay, it's one. Okay, other one is what? Tell me, what's that? If you talk with your friends, okay, they also study fluid dynamics. Actually, we learn a lot from them. I apply it to atmosphere. Okay, so what's the other difference? One is certification, and what's the other big difference? Rotation. They don't care about rotation. We care. Okay, like for example, fluid dynamics. They study fluid dynamics like when they try to design the airplane, in a wind tunnel. Okay. That they don't care about rotation. We care. Okay, or Earth rotation. So their equation they don't have F. Okay, most of them. Okay, of course some of them they study our problem. Okay, yeah, and in their equation a lot of them don't have n square. Okay. So that's the extreme case. Okay. So become like this. Reduce to the Laplace equation. Okay. Okay, Laplace equation. And that's called potential flow or irrotational flow. Okay. That's called irrotational flow or potential flow. Okay, and next topic is inertial corrected waves. Okay, what we talk about so far, we assume the Earth rotation is not important. Okay, because if we're talking about the scale or the motion is not large enough, then we can ignore F, right? But if it's large scale, then the Rossby number, okay, E over FL, okay, become smaller and smaller. Okay, then rotational effects need to be considered. Okay, and in this case, we have buoyancy force as before for corrected wave is the distortion force. Okay, you try to push it up. Okay, it expand, become colder, denser, and coming back and oscillate. Okay, that's distortion force. And now, if Rossby number is small, then the Coriolis force can also play, okay, a role to restore. Okay, it's the distortion force can bring it back. Okay. Yeah, and that will give us the inertial corrected waves. Okay, and when Rossby number is when the motion is become very large scale, then error become large, so this Rossby number becomes small. Or when your flow is very slow, then this Rossby number become very small. Okay, then we cannot ignore the rotational effects, the Earth rotation. Okay. Okay. Also, then, in that case, we have to keep this term. Keep this term, the Coriolis force term. Okay, like this term. Okay. And then we can apply the method of normal modes, okay, to W prime by assuming W prime equals W hat of G and e to the I times kx plus Ly minus omega t. What's L? The Euler number in y direction. Okay, in y direction. K is Euler number in x direction and L is in y direction. Okay. And we can substitute that into there, okay? And I want you to do a small exercise, okay? So try to substitute this into there to derive this. Okay, right now, yeah, right now. Get a piece of paper. Yeah. Okay, you make W prime equals to this, and you take ddx, okay, ddy, ddg, okay, and you take ddg, ddx, ddy, okay. You can be very honestly doing this partial x twice, partial y twice. Or you can take a shortcut, okay? Then you can do it in just 2 minutes, yeah, or 3 minutes. Shortcut. What's a shortcut? What's a shortcut? Okay. What's a shortcut? That partial t corresponding to negative I omega. Partial x corresponding to ik, partial y is il. And how about twice of partial x? Negative k squared. Okay, because it's ik, take square of ik. Okay, so you can get it done in just 2 or 3 minutes. Yeah, try it. I wanted to go around and see you, and then, okay, to see if you can do it. You cannot do it, I let people look at you. Oh, this student cannot do it. Okay, see, kind of follow me. So whenever you see partial t, you replace by negative I omega. When you see partial x, you replace it by ik. When you see partial x square, you replace it by negative k square. Partial y square, replace it by negative l square. And don't touch partial g, okay? My friends in front of the TV, okay, I also encourage you to do it. Too bad we cannot see them. It's not fair, right? They can see us, we cannot see them. Okay, if not, I think probably take your time, okay? Let's take a break for lunch. Okay, yeah. When you're hungry, you cannot do things, you know. Yeah. Okay, that's great. Everybody can do it. Okay, so now, next thing we want to do is to, it'll be similar to what we did before for the two-dimensional non-rotating fluid, okay, linear. Okay. Only thing difference is here we have rotation. Okay. So if you make that f equals 0, then this will come into here, become a squared divided by omega squared minus 1. So that reduced to that, okay. So 3.6.8 will reduce to the square w prime dg square plus, okay, then capital K is k square plus L square, okay, that will reduce to k square for 2T flow, okay, so here will become k square. And then, okay, we have this equal 0. Then inside the brackets will become a squared over omega squared minus 1. And then times the head. Okay. 这个哈叫做 head, okay? Yeah, head. Yeah, so this is W head. That's okay. Yeah. So this will become, and then this is consistent, identical to what we studied before. So what we're going to study is similar to before, except this parameter, this coefficient is more complicated. Okay. So now what we're interested is, remember when we have dw squared dg squared plus m square w head. Okay, so this is m square. Okay, and now m square becomes this more complicated form. Okay, so I want to say m square is because if m square is positive, you have one type of solution, one type of wave. If m square is less than 0, you have different mathematical solution. Okay, yeah, so that's what we're trying to do. So now, for this is This is non-rotating. Okay, flow. Okay, don't say non-rotation. Don't say irrotational. Okay, because irrotational means that irrotational means that the n square is not important. Buoyancy force is not important. Okay, like a potential flow, that's irrotational. Okay, yeah, and of course, in English, irrotational probably can also mean this, but the problem is the fluid dynamics already use that terminology. So we use non-rotating. Okay. So irrotation already has specific meaning. Okay. Irrotational means if this is 0, very small, okay, irrotational. Okay, because buoyancy is not important. Okay, extreme case, potential flow. Okay, so anyway, so m squared greater than 0, m squared less than 0, then you have different type of solutions. Okay, for m squared greater than 0, then this one will be sinusoidal. Solution will be sinusoidal in z direction, vertical direction. Then that means wave can propagate vertically. So this is vertically propagating wave. And if less than 0, then we have two solutions. One is amplify with height exponentially. That's unphysical. Okay, if disturbance is near the surface in the lower level. And so we choose that one, decaying exponentially with height. And that we call evanescent flow. Okay, so but now, before it's very simple because it depends on n squared greater than omega square or n squared less than omega square. Depends on that. Okay, now it's more complicated because beside n and omega, we also have f. Okay, so situation become more complicated. Okay, but idea is the same. So now m square is equals to k square and then n square minus omega square divided by omega square minus f square. Okay, so now you have more situation. Okay, so for example, if n square is greater than omega square greater than f square, then m square is positive, and then we have vertically propagating wave. Okay, but then there are many situations like n square could be greater than omega square, but omega square could be less than f square. Okay, so you have different kind of situation. So that's what we're trying to do to identify different flow regimes based on those three parameters. So now we have three parameters: n, omega, and f. Before we only have n and omega. So now, suppose we did this k square times n square minus omega square and divide it by omega square minus f, this one. Okay, that m square equals this, then we have this. Okay, and then in this case, okay, no matter what is m, you always can write a general solution. No matter what m is, no matter it is positive, m squared positive or m squared is negative, we always can write the solution. Okay, this one mathematically doesn't matter the physical meaning. Okay, like if you show this equation to your friends measured in mathematics, okay, they say, wow, no problem, that's okay, piece of cake, okay, 真简单, okay, piece of cake. So they will just write the solution, okay. But for us, it's more than that. Okay, we need mathematical solutions. Also, we have to understand the physical meanings. Okay. So mathematically, this has no problem. W hat, okay, of G will be equals to a coefficient times e to the I mg plus b e to the minus I mg, like that. Okay. So if m square is greater than 0, that means m will be real, right? Will be real. So it's real. So then this will give us cosine mg plus I sine mg. So vertically, you have the disturbance. Okay. That's why we call it vertically propagating wave regimes. Okay. And if m square is greater than 0, like here, okay, then m square, okay, then that implies m is imaginary. Okay, imaginary because it's less than 0. So then m can be written as I, for example, times n, and this n is real number. Okay, so now you multiply this into here, then this W hat of G what becomes A e to the minus ng, okay, plus B e to the ng. Okay, so we have two different type of solutions mathematically. Okay, so now, okay, we are going to determine, okay, what's the relationship between here, n, omega, and f. Okay. Yes, question? No. Okay. Okay, so it's defined like this. Right. The wave properties depend on the sign of m square, and wave regimes may be summarized as below. Okay. So this is from table 3.2 of Dean 2007 book. That's it. This book. Okay. Yeah, this book. Okay. One time I have a student visitor, and then he saw this book on my desk, and he asked me, "Oh, is that you?" I said, "No, it's just same name. This guy just have same name as me." Okay. Okay, let's tell you a joke. Okay, so table 3.2, talking about dispersion relations and approximated equations for the W prime for mesoscale waves in different flow regimes. Okay, so now the complete governing equation in terms of W prime can be written this way: 3.6 and 6. Okay. I think our lecture is getting better and better, okay, because I talk more about the jokes, right? Yeah. And my voice is kind of getting better, okay. I guess I don't know, last night I didn't have much sleep, but still can speak loudly. So. Okay, so we have this, and then dispersion relation, okay, right, that's this M, okay, you can. Okay, because you can date same as before. Okay, so you can date W hat of G equals to W naught e to the I mg. So, or in the beginning, you can date W prime equals to W naught e to the I, and then kx plus ly plus mg minus omega t. Okay, so here we make two steps. Okay, first step we use just this part, and then second part we have this one. Okay, so it ends up same solution. Okay, so then ends up same dispersion relation. Okay, is like this. Okay, it's like this. Okay, k square is horizontal wave number. That's equals to small k square plus, okay, L square. And omega is before equals okay. So it can make a circle, can oscillate. Okay, but horizontally. Now, this is Coriolis force. Sorry, my writing is terrible. Okay, Coriolis force. So here, tell it like this. Okay. So then it can make a circle. That's oscillation, and so that can serve as a restoring force. Why F can be serving as restoring force, just like buoyancy force. Okay, buoyancy force, because you have buoyancy force, you because certification. So when you move up, air parcel up, expand, and then because of gravitational force, okay, because heavier, right, and then coming down, then you can oscillate. So you can go back to the origin. That's called restoring force. And why we say Coriolis force can be a restoring force, it's like that. Because you keep going, that can make a circle coming back to here. Okay, yeah, that's called, okay, yeah. And inertial oscillation, right, yeah, okay. So that can serve as a restoring force. So now we assume like this. Then if this is a case, and then what happened to m square? What happened to m squared? Positive, negative. Is it positive or negative? Look at this one. Positive. Negative. Are you sure? You get me confused. Okay. How many vote for positive? How many vote for negative? Okay, I follow you guys. Okay, okay. Taiwan is a democratic country, right? So we follow the majority. Okay, 服从多数. Okay. Okay, so this is positive. Okay, because here, oh, negative. Okay, negative. Okay, okay. So negative because this is negative, right? This is negative. This is positive, so it's negative. So we have, okay, m is imaginary. So this means m is imaginary. Okay, and then under that, okay, we have some extreme cases. Okay, so then we have which kind of flow is this? If m squared is less than 0, that's evanescent flow. That means you don't have wave amplify with height because your wave cannot propagate vertically. Okay, so this implies we have vertically propagating wave. Okay, and then under this, so this is high frequency. Okay, oh, sorry, I think I probably didn't take a nap. Okay, okay, 没有睡午觉. Okay, okay, so it is less than 0. That's evanescent flow. Okay. So then there are two extreme cases. Okay, there are two extreme cases. Okay, in general, it's evanescent flow, and then we have two extreme cases. One is when omega square, okay, is much greater than n square. So that's omega. So then omega square much greater than n square, greater than f square. If omega square is much greater than n square, of course, omega square is going to be much greater than f square, right? Agree? Agree? Okay, good. Okay, so now in that case, m square k square times n square minus omega square divided by omega square minus f square. Okay, so in that case, okay, in that case, so omega square is much greater than n square. So what this becomes? Minus, okay, negative omega square. And how about this term? Okay, omega square. So this becomes negative k square. Very simple. Okay, become very simple. Okay, so so our equation become very simple. Okay, our equation become very simple. Why? Because this means we have, remember we have the w hat square, dg square, plus plus m square, and then w hat equals 0, right? Where this? So then this m square become approximate by this one, negative k square. So this means it's d square w hat dg square minus k square w hat equals 0. Okay, hear me. This is in the wave number space. Help me to recover the equation in the physical space. What's that? Okay. K square is equals to K square plus L square. Okay. And that is equals to minus, it is equals to IK square, okay, plus let me see. No. Okay, so this equals to IK square plus IL square, right? And then negative, right? Okay, so this means partial x square, partial y square. Okay, right? Okay, so this become, and then we have negative that cancel this out. So then this will recover to this plus, okay, plus d square w dx square plus d square w hat dg square dy square. Okay, like this. But this is real space, so we don't have the head. Okay, but okay, like this. So what's this? Okay, before we have this before, that's called potential flow or irrotational flow. Okay, this same thing, except it's 3D. Okay, so that's why we say we have potential or irrotational flow, same as before. Okay, so that's the advantage of talking about the pure graded waves, because now this is easier to understand. Okay, now other extreme case is so everybody got this one here. Everybody write down this? No? Okay. Take picture. You guys all have smartphone or iPhone. Take picture. Okay. Yeah. Every time I ask students, okay, are you done? Have you copy done? He say, oh, no problem. I just take picture. Yeah. Okay. So I'm going to erase this. Okay. But I'll leave this here. Okay. I'll leave it here. Okay. So like that. Okay. So this case is potential flow. Okay, or irrotational flow. Okay. Now, second possibility is if this is much greater. If we have omega square greater than n square, much greater than f square. So these two, even though this is greater than this, but their amplitude, their magnitude is comparable. Okay, about same. So you cannot ignore one of them. When you compare omega square and n square, you cannot ignore anyone because they are comparable, even though we know one is greater. Okay, but you cannot ignore one of them. But since n square is greater than f square, omega square will be much greater than f square. So then when you compare these two, you can ignore this one. You compare these two, you can ignore this one. Okay. I guess everybody's done with this. Okay, so for this case, for number 2, okay, so n square minus omega square, we have to keep it because even though it's greater, but they are comparable in magnitude. Omega square compared to f square, we can ignore f. Okay, so that makes we can approximate m square by k square times n square minus omega square divided by omega square. So this becomes k square and then n square by omega square minus 1, like this. Okay, but n square is less than omega square. Okay, so we better to rewrite it as negative k square and then 1 minus n square over omega square. So we leave this is positive. So this whole thing is positive and we're negative. Okay, so then m square is negative, it's evolution flow. Okay, see, it's evolution flow. Okay, so this one is evolution flow. And we have this evolution flow is because rotation is not important. So we call it non-rotating evolution flow. Evolution flow. Okay, and that is same as we did before, except what? This is same as we have before. In non-rotating pure gravity wave case, except what? Except we have three-dimensional. Before is k square, small k square, now is capital K square. Okay. Okay, so now we have this covered. Now, next one is if instead of, I better come here easily because, okay, remotely they cannot see clearly. Okay, so now if we swap these two, okay, omega square and n square. So if n square is greater than omega square, and both of them greater than f square, so then we have n square greater than omega square greater than f square. Okay, then that gives us vertically propagating wave. Okay, everybody done? Oh, maybe I can write there. So facility is very good. I really enjoy it. Yeah. Okay, much better than what my school has. Okay, we don't have this very fancy, and then I can go around and follow me. Okay, so now in this case, okay, when we have n square greater than omega square greater than f square, okay, and then our m is equals to k square, okay, and then times n square minus omega square divided by omega square minus f square. Oh, sorry. Oh, yeah, it's correct. It's correct. So in that case, here, the upstairs numerator, okay, the upstairs is positive. Downstairs is also positive. The denominator, okay, is also positive. So the whole thing is positive. K square is always positive. So this is positive. So positive, no matter what, it is have the vertical oscillation. Okay, we have vertical oscillation. Okay, cosine sine function. Okay, so wave, okay, can propagate vertically. Okay, so we have vertically propagating wave. Okay, so then we have vertical propagating wave regime. Okay, yeah, it's because m square greater than 0. Okay, so then m is real. So then we have this regime. And now we have two extreme cases too. Okay, one is, okay, extreme cases. Okay, first one, if we have n square greater than omega square, much greater than f square, So no matter n, no matter omega, they both are greater than f. Okay. So in that case, okay, in that case, we have, in that case, so n compared to omega, okay, but we cannot drop anyone because they are at the same magnitude. And downstairs, this f square is much less than omega square, right? So we can ignore this one. Okay, this almost 0 compared to omega square. So then this reduced to k square, and then n square divided by omega square minus 1. And this we are familiar with in pure graded waves. This pure graded waves, vertically propagating pure graded waves without rotation. Okay, so then we give a name, we say pure graded waves. Okay, no rotation. Okay, if rotation, then we have inertial graded waves. If no rotation, we call pure graded waves. So then this gives us pure graded waves. Okay. And oh, I forgot something. I should come back here. So in this case, the governing equation is the governing equation here, okay, becomes what? Because for this case, okay, 1i, okay, 1i, then in this case, omega square is much greater than n square, okay, much greater than omega square, okay. So that means, okay, that means this one gives us capital omega square, and this is f, this n square. So these two terms are much smaller than this fourth thing here. Okay, right? Okay, so in this case, the f and the n terms, okay, is approaching 0. Okay, those terms are approaching 0. So 3.6 will reduce to the following. Okay, partial t plus u partial x, and then you have this the square w prime the x square plus the square w prime the y square plus the square w prime the g square equals to 0. This implies this guy is equal to 0. Okay, so governing equation becomes like this. Okay. Yeah. Okay. And then for this case, the governing equation becomes like this. Okay, that's pretty trivial. Why? Because in the second case, omega and n, omega is greater than n, but they are comparable, so you cannot drop anyone. But both of them are much greater than f squared. That means this f squared term, the effect is small, so the term can be dropped. Okay, and then we become this, and this is similar to what we studied earlier, except this is three-dimensional. Okay, so you become this equation. Okay, yeah, that's extreme case. Okay, now vertical propagating wave. Okay, we have these pure graded waves. Okay, and pure graded waves means n square and omega square, the buoyancy force, and okay, kind of advection, okay, effects that Let me see. Okay, so this is associated with the advection. That is this term. Okay, this term. So that means both are important. This term, okay, give you advection. Okay, and this term give you vertical oscillation, the buoyancy force. But this term, because f squared is much less than n squared term, as well as that omega term, omega squared term. So then this dropped. Okay, then we have this pure graded waves. So equation becomes this. Okay, so this is a nice table. You summarize everything in one table. Okay, and then next one, you have another extreme, because if omega square can be much greater than f square, you also can have n square much larger than omega square, and of course that means n square will be also much greater than f square. Okay, so in that case we have we have this special case like this. Okay, n square much greater than omega square, much greater than f square, like this. And then that will reduce to what? Reduce to this equation. Okay, and this means what? This means it's hydrostatic. Hydrostatic. So how do you see the static or not from the equations? I tell you a trick. Okay, a kind of a trick. So okay, so if these two terms are much smaller than this term, you drop them, that become hydrostatic. Okay, yeah. So equation like that, and you can trace it actually. Okay, of course this is a shortcut. You have to really do it to understand it. Okay, and then you have the third case, right? Do you remember? Actually, I talk about this case first, okay, and then because I follow this, okay, go back to this case. So you can have, so now you can have n square much greater than omega square, okay, like this, okay, and greater than f square. That means n square will be much larger than omega square and f square. So you can ignore these two if they are compared. I just say dW, okay, dW, greater waves. And then third case is n square greater than omega square, and both of them much greater than f square. Okay, then in that case, n square greater than omega square. Okay, so we can keep both terms, and this one we can ignore this. Okay, so that gives us k square of n square divided by omega square minus 1. Okay, so this is what? This is great waves, but it's non-rotating, same as before. Okay, okay, so here is this is same as here. Okay, we are not supposed to do it. We're supposed to do this case. Okay, so sorry about that. Okay, so now n square much greater than, so we ignore this. We ignore this one. Okay, this one we ignore almost 0. And omega square, okay, we have to keep this term. Okay, so that becomes k square times k square times n square divided by omega square minus f square. Okay, yeah. So when you have this, okay, that gives us n square, yeah, then give us the hydrostatic inertial graded wave. Okay, and the governing equation can be written this way. Governing equation. Okay, governing equation is governing equation is these two terms are much smaller than this term. Okay, and okay, so then this will become the square w dg square, and that can be combined with f term. Okay, okay, so then yeah, these two terms can be combined and with dtg term times this. Okay, and that's called hydrostatic inertial gradient wave. Okay, and then let's finish this because just one more case. Okay, if we have n squared greater than f squared greater than n squared. So I think everybody's down here. Okay, so we have the third case. Okay, we have n squared greater than f squared greater than omega squared. Okay, so in that case, m squared is equals to k squared times, okay, n squared minus omega squared minus f squared. Okay, so upstairs is positive and negative. Positive. Okay, n squared squared. So this is positive. How about downstairs? Negative, because f is greater. So negative. Okay. So that means m squared will be less than 0. That means it's vertical propagating wave or it is evanescent. The wave will propagate more horizontally. Okay, instead of vertically. Which one is? Is this vertical propagating wave or evanescent? Evanescent. Okay, so evanescent. Okay, flow. So here is evanescent flow. Okay, yeah, evanescent flow. But we have two evanescent flow. We have two evanescent flow. Do you remember here? Here, we have evanescent flow because m is imaginary. M squared is less than 0, and here we have other one. So in order to distinguish them, we call this one high frequency because omega squared is greater than others. Okay, and here we call low frequency because this oscillation, okay, intrinsic frequency is less than f squared. So we call it low frequency. Okay, evanescent flow. And then you have the extreme case, like, yes, your question. Say again?
F
Yeah.
is the largest.
Yeah.
The largest
Oh, largest. Yeah, you can have that. Yeah, but normally it's not very kind of applicable to the atmosphere. Okay. Yeah. Yeah. Normally not very applicable. Okay. So here we're talking about probably more kind of more realistic flows. Okay. Okay, so then if we have n squared much greater than f squared, much greater than omega squared, then the m squared is reduced to like this, and then the whole equation will reduce like this, and then that is quasi-Josephic flow. Quasi-Josephic flow. Okay. you probably have you can have f squared greater than n squared greater than omega squared. Yeah. And also you can have f squared greater than omega squared greater than n squared. Okay, you probably can have that. And then they probably will end up f is important, and you can have the vertical propagation wave. Then that is probably more or less related, more or less kind of related, but not quite. The kind of mixed Rossby gradient wave. But mixed gradient waves, Rossby gradient waves is with beta instead of f. Okay. So kind of particularly we don't kind of observe that kind of wave. Okay. Yeah. Okay, so that's great. Okay, so okay, we finish this chapter 4. So it go very quickly, huh? Yeah, it go very quickly. Yeah, but it looks like people are okay. Yeah, okay. So we can go with this speed, and then next chapter will be the diffraction level and critical level. Okay. It's like we're going very fast. Yeah. Maybe we should stop here. Okay, so next topic is also very important. Okay, even though it's a general gradient wave type of thing, but without that, you cannot fully understand the mountain waves. Okay, because the mountain waves is a special category, special case of the general gradient waves. Okay, so without the understanding, when you see some gradient waves which are reflected, if you don't have the background, you cannot understand. Okay, that's why I put this in here. Okay. Okay, so first, the atmospheric waves may be reflected from the Earth's surface. Okay, the surface of a fluid. Okay. And the surface of fluid, like if we have say if we have a shallow water system, okay, at the top we have the shallow water wave, okay, that's surface wave, okay, and that's part of the gradient wave, okay, and or internal interface at density discontinuity. So say if, even though it is stratified fluid flow, but if say we have very stable layer near the surface, and then there's stable on top, then okay, you could have wave diffraction. Or on the other hand, if you have a very stable layer and on top of the kind of regular layer, okay, like a tropopause, okay, Pendleton, it's tropopause, okay, 对流层顶, okay, a tropopause above is stratosphere, and that's very stable. So n squared is much greater than, probably 2 or 3 times larger than in the, okay, troposphere. Then wave can also be reflected. Okay, so that's important to understand. Okay, because almost everywhere you have the reflection. Okay, if the atmospheric structure, such as n squared, n and u, okay, sometimes you have not only n, sometimes your n probably is more or less constant, but your u has a geometrical change that can also cause the reflection too. Okay. Okay, so say if n is constant, but you have strong shear that can change, can have the reflection. Okay, then gravity waves may be reflected from and or transmitted through the interface at which rapid changes in atmospheric structure occur. Okay, so no matter it is the discontinuity or geometrical change of N or U or combined, you can have gravity waves, okay, reflected, and some of them probably transmitted, and you have to know, okay, that properties, okay, the characteristics. Otherwise, no matter you are doing research, okay, by observational analysis, or by modeling, okay. In modeling, you could produce very beautiful pictures, and they are probably as complicated as the atmosphere. So if you don't have the background in dynamics, you will get lost. Okay, or you can just show people, oh, it's so pretty, okay, so powerful, the model is so powerful, computer is so powerful, okay, and we can mimic the real, okay, atmosphere, okay, motions and processes, but you may be stuck if people ask you some critical questions, okay, and that require you to have the knowledge about dynamics. Okay, so now let's consider a very simple case. Okay, very simple case. Okay, like this one. Like this one. So say if we have an atmosphere structure like this, and here is the height. Okay, and so let's say if we have a stable layer here, we call N1, and we're N2 here, like this. Okay, and remember, we have this, just consider 2D linear. Okay, and non-rotating. Okay, and inviscid. Okay, and adiabatic flow. Then we have the following. Remember, we have the following. We have partial t, partial u, partial x square, and then we have the square W prime, the x square plus the square W prime, the g square, 2D, so we don't have partial y. Okay, and then plus n square, the square W prime, the x square, like this. Okay, so that's what we started in the previous chapter. Okay, I think we probably, do we have another one? Yeah. Oh, downstairs. Upstairs. Oh, okay. So if we did, probably let's wait because he needs to listen to this too. So this one probably. Oh, there are some here. How many people?
10.
Oh, not bad, right? Yeah, not bad. Not bad. Better than yesterday. Yeah. Hmm? Oh, thank you very much. Okay. So this, like before, okay, I go with this quickly. So that W prime, oh, this is pretty good. Yeah, it's pretty good. Equals to, okay, equals to W hat of G e to the I of kx minus omega t. Then that reduce, okay, convert, transform this equation in the physical space to Weyl number space. Okay, if k, here we only consider one k. If we consider many cases, many k, then we'll be using Fourier transform. Okay, but there we just use normal mode approach. So that will give us square W hat dg square plus n square minus omega square minus 1 times k square, and then W hat equals 0. Okay, that's correct, right? Okay, all right. So now let's make one more assumption. Okay, so assume, okay, U is equal to 0. Okay, to make it simple, so help us to understand the basics. So like this. So then what happened to omega square? Will become small omega, okay, square, like this. Because omega is equals to defined as small omega minus ku, right? Right. So this is gone. Okay, so then this will become, the equation will become d square W hat dg square plus, okay, n square divided by omega square minus 1, and then k square times W hat equals 0. Okay. No, we will make more assumptions. Here we don't. Okay. Here we just, to make it simpler, we make assume this. Okay. One more assumption. Okay. So we have this. Omega square. Okay. So if we have omega here, okay, but remember here actually there are two equations because we have two there. They have different n1, n2. So actually this equation, okay, the common equation actually becomes 2. Okay, so with this square, and so say this is h, g equals to h. Okay, this h here. So omega W hat dg square plus n square over omega square minus 1 k square W hat equals to 0 is, it will become n1 for g less than h. Okay, and for upper h will be governed by other equation. The square omega W hat dg square plus n2 square minus omega 2 so 1, and then k square W hat equals 0 for g greater than h. Agree? Yeah. Okay, now everybody got this? Okay, so now a little bit more complicated. We have two equations because one governing the lower layer response, other one upper level response. Okay, so now for, let's call it layer 1. Okay, so layer 1 we have n2 square greater than omega square, right? See here, n2 greater than omega. Okay, so which kind of wave is this? Wave regime? It's vertically propagating wave or evanescent? Vertically propagating wave. Okay, so you have vertically waves. How about there too? N1 square greater than omega square. Okay. Same thing. Right. Same thing. Same thing. Same thing. So that means if say we have flow, so say you have flow here. No, we don't have flow here. Okay, so in this case, you have disturbance, then that disturbance will trigger, will produce the greater waves, vertically propagating waves. Okay, but both there will produce the waves propagating vertically. Okay, no matter it's up or down vertically, both there, so there's no problem. It's just okay. It's just because N1 and N2 are different. So then when they oscillate, they are oscillate different frequency. Okay, period. And so then they just change the characteristics, but they are both go up. Okay, so in this case, there's no reflection. Okay. Okay. Omega. Okay. And of course, we can call it, we can probably just, because we wanted to have many omegas, so we give a name. We call it omega 1 here. So here, we give 1, we give omega 1. Okay. Okay. Okay, now we consider another case. Okay, so another case is, say, omega 3. Omega 3. Okay, so for this case, omega 3 compared to N, okay, so compared to like N1, so N1 is less than omega 3, right? N1 is less than omega 3, N2 also less than omega 3. So N1, both N1 and N2 are less than omega 3. Okay, so when N1 is less than omega 3, that means the advection, okay, is larger than the vertical buoyancy. Okay, so then the wave cannot propagate up. It's evanescent flow. Okay, so this is both are evanescent. So it's okay. There's no reflection. Okay. So this implies no reflection. Okay. So this is case 3. Okay. This is case 1. Okay. How about case 2? So now if we have the omega, we call omega 2. is in between N1 and N2. Okay, then what happened? This one is not good. Okay, so in this case, in layer 1, oh, sorry. I think layer 1 is supposed to be N1, right? To be N1 here. But conclusion is same, so don't worry. You just change it. Okay. Layer 2 is N2. Okay. So layer 1 will be N1, and then omega, oh no, N1, and then omega 2, right? So in layer 1 here, N1 is greater than omega 2. Okay. And for layer 2, N1 is less than omega 2. So which kind of wave is this? Vertically propagating wave. Okay. So here vertically propagating waves. How about upper there? It's N2, right? N2. How about up there? N2 is smaller than omega 2. Okay, that will give us m squared to be negative. Okay, that gives us which kind of regime? Evanescent. Okay. So then what happened? What happened is, if we have wave generated here, it can propagate up, but then here become evanescent. So it cannot propagate up. So where the energy goes? Reflected. So in this case, we have reflection. Whoa, terrible. My writing is terrible. I don't know how to improve it. Wave reflection. I cannot even write clearly. Yeah. Reflection. Okay. Yeah. So wave will be reflected. Okay. Wave go up, will be reflected. That's called reflection level. And this is called reflection level. So we are done with this. We apply the method of normal mode, okay, and then, okay, we apply this, and then we get, okay, 2 layers. I just keep the original form, n squared over omega squared mass 1. That gives you m1, okay, m2 squared, okay, and so then we have these solutions, okay, and that solution is depending upon your m1 square is positive or negative, m2 square is positive or negative, okay, and then you have to have g minus h there, okay, because this is greater than 0. Less than h. For the lower layer, for the upper layer, g greater than h. Okay, so we have solution like this. Okay, so there we write down the solution like that. Okay, and you can prove that is a solution. Okay, you can substitute them back to the governing equation, original governing equation, and then to see. And then we have 3 possibilities. Okay, Ni greater than omega, for I equals to 1, 2. Okay, that's this one. Okay, case 1 here. And then case 2, case B, is omega, okay, greater than ni, okay, n1 or n2. That's this case, okay. And then case 3 is omega is kind of in between omega 1 and omega, in between n1 and n2. That's this case. That's, I call it case 2, okay, here. Okay, so I think I already explained this, okay. So, okay, so then you can have this kind of diffraction. And this kind of case is observed, like for example, at night, then you start to have the radiation back to the atmosphere, and then near surface, there will be cooled down. And then you have that case. And other case is when you have thunderstorm. Okay, you got rainfall, and rainfall coming down, although the cloud base is unsaturated. So then you got evaporation. Okay, so evaporation, what's going to happen to the environment? Cool down. Okay, so be colder, and colder will make it more stable. Okay, so near the, okay, so you could have a layer here, okay, which is N1, N2, and then in that case, you can have like this. You can have this, okay, case. Okay, let's just give you example. And but the object, okay, on the other hand, if in the afternoon we have strong heating, okay, radiative heating near surface, then will be object. Okay, so we could have this kind of situation like this. Okay, so this is stable in the boundary layer, for example. Okay, so this could be okay, like in the afternoon. Then we can have a situation, and also we can have a situation like that. Okay, like that, but the discontinuity or the interface is at much higher level, that is tropopause. And this always happen, always there. Okay, okay. So you could have situation of N2 less than N1. That may occur. Okay, in the infinity. Okay, that means in the neighborhood. Okay, in the vicinity of a thunderstorm, in which the lower layer is more stable due to the evaporative cooling associated with rainfall. Okay. And the opposite situation often occurs when a mixed boundary layer is produced. Okay, so you can have different situations, and they can all produce some kind of diffractions. Okay, and this is called diffraction level. So if we look at this case, particular interest in this case, then we can work out the solutions. Okay, we can work out solutions, and so you can have the solution already. We have this solution already, right? In upper layer, in the lower layer, we have two solutions. Okay, so now, how many coefficients here? How many? 4. We're in trouble. Okay, so that means we have to solve this in that. We have to solve this completely. We need to find, okay, A, B, C, and D. So we have to find 4 conditions. Okay, and we already know. We have upper boundary condition, we have lower boundary condition. Okay, that will give us solution. Okay, to help resolve the problem, but we still need 2 more conditions. What are they? there will be the boundary conditions as we call interface boundary conditions. Okay, so as an interface, we need two interface boundary conditions. And what are they? W got to be continuous, constant. W, okay, yeah. Okay, so first, W prime has to be continuous. So down below has to be equals to right above. Okay, so your W at layer 1, okay, and at GH. Okay, let me see. Let me write it more clearly. G equals to H has to be equals to W2 of G equals to H. At H here, right above should be equals to right below. Okay. And or you can write it this way. Yeah, I think you understand what I'm talking about. So here W1, okay, or another way to say, to write it the same way, I think you understand what I'm talking about. W1 W at H plus is equals to W at H minus, just below, just above. Okay. Yeah, you have different ways to say it. Okay, I probably have different ways to say here too. Okay, so you need this, and then second condition is yeah, partial W, partial G. Okay, should be continuous. Partial W prime, partial G should be continuous. Continuous. Okay. Across G equals to H. This one too. Okay. And one of them, okay, you can derive that. Okay, you can derive this. You can derive this why you need this. Okay, and one of them is called the kinetic boundary condition. Kinetic boundary condition. Another one is called the dynamic boundary condition. Okay. Yeah. So then, in that case, then we can based on this solution, but not fully resolved because we need to find A, B, and C, D. So upper boundary condition, lower boundary condition, and then two interface boundary conditions will help us to resolve the solution completely. Okay. Okay, so first, if we apply the lower boundary condition to 3.7.6, that two equations I just show you, then will become like this. Okay, will become like this. Okay, so we have this, right? So, okay, first lower boundary condition. Okay, so apply the lower boundary condition. Then Okay, low boundary condition, if there's no mountain, okay, W prime, okay, probably head, because we're in weird number space. Okay, if G equals 0, would be equal to 0. Okay, that's low boundary condition. Okay, without terrain, no mountains. Okay, and this not to worry about mountain right now. Later we are going to, okay, I'm going to talk about, discuss about, okay, when you have mountain, what's the low boundary condition will be. Okay, so this like this. So then, which one should we apply to? 3.77 or 3.76 to apply this one? 3.7.6, right? Yeah, okay. So 3.7.6 will imply that 1, okay, at G equals to 0 will be equal to A times e to the I m1, and then minus h, okay, plus b e to the what? Minus I m1 times minus h. Okay, but this has to be 0. Okay, and this one can be written as A e to the minus 1 minus I m1 times h, and then plus b e to the I m1 h. Okay, like that. So this means what? This means we can move one term to the left-hand side and then resolve it. Okay, so you can do either way. You can express A as function of B or B as function of A. It's up to you. Okay, so let's see what we have here to be consistent. Okay, so we have here like this. Okay, number 1 equals to B, so that means we make A equals to A e to the minus I m1h equals to negative B e to the I m1h. Okay, so this means A is function of B. We just use this way. You can do other way too. And then it will be equals to B e to the, wait, what happened? Which one? Something wrong. Oh, yeah, it's okay. It's okay, because here, yeah, we have minus B e to the I m1 h, but divided by this one. Okay, divided by e to the minus I m1h. So this gives us negative B e to the 2I m1h. Okay, and once you have this, we can substitute, okay, into the equation W1. So for G greater than 0, less than H, that's the first layer, lower layer, then we can substitute A into here. Okay, A into here. So then that means W1 head will be equals to minus B e to the 2I m1h. Okay, and then times e to the I m1, and then G minus H. Okay, so we apply low boundary conditions to give us the relation between A and B, and then let A equals to function of B, and then substitute, and then we get rid of A. Okay, so that gives us this, and then and then plus B e to the mass I m1 and G mass 1, G mass H, like that. And then we can pour B out and then desaturate, and then that will give us this equation for W1, okay, in this layer, okay. And then in the C2 upper layer, we have this. Okay, we just did N2 equals to IM2. So, okay, we just like this. And then now we have these two equations, but we only have three coefficients because we already applied low boundary condition. So that helps us to get rid of one coefficient, that's A. And now we only three, we need three conditions. So one will be top boundary condition, and another two will be interface boundary conditions. Okay, so I think I better stop here. Okay, and then continue next Tuesday. Okay, yeah. Okay, thanks.